we go. Not to put like a damper on the start of things, but this is how much I care about your mathematical success in the future. We can't just brush it under the rug. All right, here we go. We're talking about functions, and we're going to be doing beautiful things to these functions. We're going to be combining them using mathematical operations, adding, subtracting, multiplying functions, dividing functions. And then, of course, we're going to be investigating, determining the domain and the range of these functions and the resulting functions. But then we're also going to be doing other things to these functions, things that you don't necessarily know about right now. And I told you, I gave a little foreshadowing in the past when we looked at the line y equal x, and that's going to be proved to be very important for this unit. It's a short unit, very short unit, but it's heavy duty. Okay, so let's first start off with something simple, and let's talk about finding the domain of real valued functions. So we know how to find the domain of real valued functions. So if I have the real domain of a function f, I can denote it with this d with the subscript f. That's a notation we've seen before. And all it is the subset of real number inputs for which the function is defined. This is nothing new. We're just formalizing some definitions. So if I have a function and I'm talking about the domain, those are your input values. Now, if I'm more particularly am looking at a polynomial function, the real domain, and when I say the real domain, because we know we can have imaginary values when dealing with certain types of functions. So I'm only looking at real values. The real domain of a polynomial function, this was an extra credit on one of your tests, is what? All real numbers, right? Polynomial function. It goes on forever and ever and ever. So it's all real numbers. Now, we've also looked at rational functions. So how do I determine the real domain of a rational function? This is where it gets a little bit more interesting. The real domain of a rational function, which we looked at the denominator and we determined what values of x in the denominator made it 0, right? That's where we were looking at domain restrictions. So to find the real domain of a rational function, you first start with all your real numbers, and then you subtract any domain restrictions that make the denominator 0, right? So we have to exclude any values of x that make the denominator 0. So we start with real numbers, and then we subtract out any values that make the denominator 0, right? So we're looking for what made the denominator 0. This, again, is nothing new. We're just formalizing it. Why? Because now we're going to get to real valued radical functions. And if you remember back to real valued radical functions, this is our radical function, right? I see a square root symbol. I see a radical symbol. But what do we have to pay very close attention to? We have to pay close attention to that root index. Because remember, if the root index is even, what do we have to make sure we pay attention to? We have to make sure that the radicand is positive, right? If the root index is odd, we can take an odd root radical, right? Root. We can do that. So it's all real numbers. So let's say I give you some functions. So here we have some functions, and I ask you, just tell me the domain. So you're given a function, you have to recognize what type of function do you have, visualize it in your head if you have to, or do a quick little sketch, and let's see what the domain of each of these is. So what type of function is this? F of x equals c. When we were building our library of parent functions, what did we call this? A constant function. That's right. This is just a constant function. So what does the graph of a constant function look like? It's just a horizontal line. Yep. So if I have my constant function, let's say looks like that, what would we say the domain of f would be? That's right. Okay, now let's look at the next one. This is another type of function that we've worked with. In particular, what type of function is this? It is a quadratic function. What would the underlying, this is a little foreshadowing, what is the underlying parent function? Y equals x squared. Good. That's just future reference. So what does the graph of this look like? It is a parabola, right? And, you know, I'm not going to do a complete sketch, but if I looked at the parent quadratic function, it would look like that, right? Or perhaps like this if it was reflected across the x-axis. What would the domain of this and any quadratic function be? Again, all real numbers. Good. So we're looking at functions. We're being able to recognize and classify it. But then we can talk about the domain. So now looking at this next type of function, what type of function is this? A rational function. So this is a rational function. So now to be able to identify the domain of this rational functions, we have to look to see what makes the denominator 0. So I'm looking in particular at this denominator, and what would I do to that denominator? I would factor it, okay? So what are the two factors?
X minus 3.
Beautiful. And so I would set each of those equal to 0, and I'd say, all right, this function, this rational function is undefined when x equals 3 and x equals -4. So I would say that the domain of f is all real valued x's, right? So x is a real number, but x cannot equal 3 or -4. And that is valid set builder notation, right? This is set builder notation. Okay, if I wanted to write this using interval notation, what would it be? -4.
Union, -4 on
+3 union.
Union, positive 3.
Beautiful. Okay, and we should be able to go back and forth among different notations. All right, looking at this next one, what type of function is this? It's a radical function. And what would we investigate here? What would we first have to pay attention to? The root index. So what is the root index?
2.
The root index is 2. If I don't see it, I know it's square root. So I have to investigate the radicand. So this means I need to investigate the radicand because the restriction is that that radicand has to be greater than or equal to 0. Otherwise, I'm not talking about real values in the domain. I'm looking at, you know, imaginary numbers. So I would just go ahead and solve this. Now, do we remember what we have to think about with respect to this? What values of x? X could be what? This is an inequality.
Would we
Oh, this is positive one, sorry.
and say like what it can?
Do we remember how we did these? Is this an and or an or?
Oh, and isn't it?
Greater or than, right? So x can be greater than 1 or greater than or less than -1. Now, how could I easily write the domain for practical purposes? I could easily say, well, x is any real number, and then I could just take this, oops, and put that over here. That's allowed. That is fine notation. There's nothing wrong with that. But to be able to write it using interval notation, I would need this. If we're having trouble with this, maybe we need to review how we solved inequalities, right? Okay, the next one is also a radical function or radical equation, let's just say. Again, if I look at the root index, I see that my root index is 2. So since my root index is 2, I have to look at my radicand and make that positive. Now, look at this one. X squared is greater than or equal to -1. What can you tell me about that? What values of X would make this true? Big picture. Let's look at the big picture. I'm looking for an X value that if I square it is greater than or equal to -1. This is always true. Yes. So the domain of F in this case is all real numbers. Big picture. Don't just start solving things algebraically. Think. Okay, looking at this next radical equation. At this point, I notice that I have a root index. Oops. So it is odd. So what can you tell me about the domain of this function without doing any work? It is all real numbers. So again, there's those certain things like when we looked at certain inequalities, we should be able to recognize if it's always true or never true. There's no work to be done. Okay, now what type of function is this next one? It's complex. Yeah, this is complex. It's rational, but it's more so complex. So what does that mean since this is complex? That means I have two denominators, right? Potentially. So I first want to look at this. So if I investigate 4 over x minus 1, from that, if I were to solve this, or actually solve it for when it's equal to 0, right? I want to set the denominator equal to 0, so I get 4 over x equal 1. What does x equal? So I know immediately in my domain restrictions, x is a real number, but x cannot equal 4. But is there anything else I have to worry about? Just look at this. Look at this in general. I see a fraction. X can't equal 0 either, right? Does everybody see why it can't be 4 or 0?
Yeah. Okay. Because 0 would make it undefined.
From the get-go. But then when I actually simplified that denominator, you know, I'd also have to look at.
Wouldn't that just make -1 the denominator?
No, because you can't have a fraction with a 0 in the denominator.
I'd have to get a common denominator, right? Oops, did I skip one? No, that was it. All right, so that's if I just give you one function. I give you one function, you identify the domain or any restrictions it has on it. Now, let's go ahead and perform some arithmetic operations. So now we're looking at combining functions using the algebra of functions. So what do I mean about arithmetic operations? I mean taking the sum, taking the difference, taking the product, taking the quotient of two functions. So I'm giving you two functions and I may tell you, hey, add them. Take the sum. I may say, find the difference. I may say, find the product. I may say, find the quotient. So given two functions, you have to be able to perform these arithmetic operations on these functions and then state the domain. So performing the operation shouldn't be the hard part. Should not be the hard part. Okay? Again, on the quest, when is your quest? I moved it to Monday to give us a little bit extra to make sure that we can do the everything. Okay? It's now Monday. You'll need to be able to recognize whether I give you a sum and know to add or multiply or divide or subtract. I may use words. If I use words, then you need to understand that I'm looking at f plus g with the input x. How do I do that? I just take f of x and I add g of x. That's it. So if I give you two functions, if I give you, let's say, f, what type of function is that? F of x equals 3x minus, it's linear, right? This is a linear function. What is its domain? It is all real numbers. Okay, and then let's say I go ahead and give you g. What type of function is that? Okay, and what's its domain? Okay. So if I ask you to take the sum, I may give it to you in this format. You need to know that that means the same thing as this. This is just an abbreviated version. And to find the domain, what am I looking for? What does this symbol mean?
The intersection.
It means the intersection.
Where the points that they share.
Share. So that means I'm looking at the intersection. So this symbol, if you recall, means and. It is the intersection. It's what they share. Okay, so how do I do that? Well, I'm going to take f of x. My f of x is 3x minus 2. And I am being asked to add that to g of x, which is x squared minus 2x plus 4. I'm just adding the two functions together. So all I'm doing is combining like terms. If I combine like terms, what is f plus g of x? Combine like terms and put it in standard form. What do I get? Yes.
What would you name the function like?
No, it's just sum.
Oh,
Now, if you want to introduce a new one, h of x is f plus g of, that's fine.
okay.
And what is the domain of f plus g? All real numbers. Good. I may also ask you to find the difference of two functions. So the difference, let's say f, minus g of x can be written as f of x minus g of x, which just means, and the order matters, so f of x minus g of x. I have to subtract every term of g of x from its like term in f of x. And so the difference, f minus g of x, combine like terms. So again, first distribute and then combine like terms. Tell me what the difference function is.
X squared
Negative x squared plus 5x minus 6.
And the domain of f minus g, so I'm just showing a little subscript, f minus g is what?
Oh,
Again, all real numbers. How do I know that? Because it's just the intersection. Okay, let's talk about what happens when I am multiplying. I'm taking the product of two functions. So in this case, you are being asked to find the product. So it can be written as f times g of x, or separated as f of x times g of x. F of x, again, we said was 3x minus 2. This is times g of x, which is x squared minus 2x plus 4. So how am I going to do this? I have to distribute, right? I'm taking 3 and multiplying it by each of these. Then I'm taking negative 2, multiplying it by each of these. Once I distribute and combine like terms, do that and tell me what f times g of x is.
Yes, minus 4x squared.
Minus 8x squared.
Plus
Plus what?
16x.
16x.
Excellent. And so the domain of f times g is
All real numbers.
all real numbers. Excellent. And last but not least, and again, just to point out, it's still the intersection. Last but not least, let's talk about what happens when we try to take the quotient of two functions. So in this case, I'm looking at the quotient. So that is f of x, or f of g of x, is f of x divided by g of x, which just gives me a beautiful rational function. So this is a complex fraction, right? It's just a nice little rational function. And what would you notice? Is the denominator factorable? It is.
No.
No. So how on earth would I find those values of x? Well, but I can't solve it. So how am I going to find?
Quadratic formula.
Yeah, that's right. You would use the quadratic. We're not doing that now. You should already know how to do that. Quadratic formula to get, and you will get complex roots. Okay. So in this case, if I ask you for real valued, it can be any real number, but we'd have to exclude those complex roots, right? So all real numbers are okay, but complex ones may not be.
Oh, so you wouldn't have to say all real numbers. You'd say.
Because complex numbers aren't real.
Okay.
All right, now take a deep breath. Adding, subtracting, multiplying, dividing functions is easy. Taking the composition of functions is super fun. Okay? So forming composite functions. Taking the composition of two functions. This isn't hard once you do two of them, it's easy. Composition of two functions. So I am composing function f with function g. To represent that, I would say f of open circle g. So that notation here, f open circle g, not close. Close means multiplication, right? This little open circle means you are taking the composition of two functions. So I would give you this notation and you would know that I am composing f with g. F composed with g. Order matters. So I'm going to say here, order matters. F composed with g is not necessarily the same. Well, in only one instance, it's the same as g composed with f. Okay? So f composed with G, function f composed with G can also be written as f of G of x. So this also means composition. F of G of x. Now, what am I doing? I have two functions, and you kind of look at it in the sense of you work from the inside out. So I have domain values of x. My input from the inside is x. That is my input to my function g. Okay, do you see? If I just look at this part here, I just have g of x. So I have domain values x, which I'm feeding into the function g. What is that going to give me? It's going to give me the output g of x, right? Which we know to be y, right? So once I've done that, I've taken domain values of x, I've fed it into g, I got my output g of x, which is just y. That then becomes the input to my function f. This becomes my input to my function f. So the output I get from putting x into g gives me my input into f. So what am I getting? I'm getting f of g of x. So I'm getting the output here. So it's kind of like a little machine. You start from the inside, you have domain values, you feed it into x, you get output. You take that output, then in turn feed it into f. You work from the inside out. All right, so let's take a look at this. Now I say that when we make the diagram, but it's going to sound contradictory when we actually start algebraically trying to take the compositions. So you've been given the same two functions. You have f, which we said was a nice linear function. We have g, which was this quadratic function. What I'm asking you to find is f composed with g, f of g. Then I'm asking you to find g composed with f, g of f. Then I'm asking you to find f composed with itself, f of f, and then g of g. All right. So I have f composed with g. F composed with g. F, that's why order matters. F is on the outside, so it's the big function that I'm feeding g of x. Oh, I did that backwards with the colors. F of x is on the outside. G of x is what I'm feeding into it. So these notations mean the same thing. So they both represent composition. One is with the open circle and the other one's with a function of a function. So f of g. So the first thing I'm going to do is I'm going to write f of x. I'm going to start with f of x because it's the big one on the outside. So f of x is 3x minus 2. Now, what is going to be my input into x? My g of x, right? So I want to feed g of x in as my input to f. Do you see how I'm starting here and I arrive at this notation? So that means everywhere I see an input, I'm going to feed in g of x. So instead of x, I'm putting in g of x. Start with the big function on the outside, write it, and then show how you're feeding in the other function. Do you see how I just removed the x and replaced it with the other function? Now, what do I have to do? It's easy from there. Just distribute. So that would give me 3x squared minus 6x plus 12 minus 2. Combine like terms so that you can give me f composed with g. What would it be?
Oh, it would be 3x squared minus 6 plus 6x plus.
That's it. Not hard. Now, let's go the other way. Since I said order matters, let's see if that's necessarily the case. G is now composed with f. So the big outside function is g, and I'm feeding into g, as the domain values, f of x. So I'm going to start with the big function g. Oops. And everywhere I see an input, I'm replacing that with f of x. So that is going to be, and then f of x is just 3x minus 2. So how am I going to approach this? Well, what do I have to do to this? I have to FOIL it. I sure do. Okay, so if I FOIL that, that will give me 9x squared minus 6x minus 6x plus 4. And then what do I do to this? I just distribute, right? So that's minus 6x plus 4. And then I still have this plus 4. So if I combined everything, all my like terms, for g composed with f, what is my final function in standard form?
X squared minus 18x plus 12.
Excellent. So there will be the composition. So if you notice, f composed with g in this case didn't equal g composed with f. They are not necessarily the same. So I want to point out f of g of x does not necessarily equal g of f of x. Not always true, but it can be. Oh, I love the way you're thinking. We're back.
Like on that quest. Like that
The only multiple choice we have.
No, I can't read what that says.
That f composed with g doesn't always equal g composed with f. It can, but it's not always the truth. We've just shown a counterexample where the composition of the same two functions in different order isn't the same.
What do we like? What do we use this for? Like, what's the composition give us?
It mainly is used in modeling. So let's say you have a mathematical model. Well, it's used in many different things. So one example is if you have something that has to happen first, right? Be it that anything that you can mathematically model. Let's say you're going to space, right? And you have to get there first, right? So these things have to happen first. I mean, this is a big global picture that I'm just trying to show why you would have to feed something into it. What happens there can't happen until we get there, right? So I may have a model that has certain restrictions on its input that have to happen. And then once I get there, I'm going to have only the output of what happened in this model to take with me to the next model. That's a big, big, big global picture. So that's not really a tangible example, but I wanted you to kind of get an idea that, like, if you're taking resources somewhere, you know, the resources that you're taking has to satisfy this, and then in turn, whatever is left has to go into the other one. It also occurs a lot in theory with different surfaces that you work on. Like we live in 3 Euclidean space where it's, you know, nice and planar and or in 3D space, right? But there's surfaces that have different geometric properties. And so when you're dealing with those and you have certain things occurring in one space, you only have the result of what's happening in that space to feed into another space. I know that's very abstract, but it's used a lot. It is used a lot. Okay, so let's go ahead and for practice, let's just compose f with itself. So I have f composed with itself. So that means I start with f of x, which was 3x minus 2, and then if I want to feed in g of, oh no, I feed back in itself. And then I just distribute. I get f composed with itself, which is just 9x minus 8. And I can do the same thing with g. Compose it with itself. So I start with g of x. And I don't remember what the function was. G of x was x squared, x squared minus 2x plus 4, and I want to feed g of x into it. So this is algebra. So now in this case, what am I doing? I'm multiplying a trinomial times itself. So I'm going to leave that as an exercise for you. We have time at the end of class. If not, look online for the answer. Or I can give you the answer. No, I won't give it to you yet. So do practice that. All right, now we learned what it means to take the composition of 2 functions to find a composite function, the result of taking the composition of 2 functions. How on earth am I going to determine the domain of the composition? So the domain of the composition, bless you, domain with the little subscript f of g, is just the domain of g. So the domain of the input, right? Because we know this f of g of x equals f of g of x. So we start with the inside. And then we subtract from that any domain restrictions on the output. Right? Because anything that can't go into G will not ever go into F. So we have to first look at the domain restrictions on G, and then look at the domain restrictions on F. Now, what does that mean? That means X has to be in the domain of G, and G of X, the output, has to be in the domain of F. So if I have these 2 original functions we've been working with forever and ever and ever, and you are being asked to find the domain of the composition, we can recall what we just did, that the function f of g was 3x squared minus 6x plus 10, which in fact is just a quadratic function. Now, there's a couple of ways we can look at it. I like to start with the everything and then start subtracting things. So I personally write it a little bit differently and say I start with all real numbers. And then I'm going to subtract the restrictions to G. And then I'm going to subtract the restrictions to f of g of x. That's how I like to look at it. Now, we started with all real numbers. Do we have any restrictions on G? No. Do I have any restrictions on the composition? So I have just all real numbers. Let's look at another example. What type of function is f? It's a radical. F?
Oh, no, quadratic.
It's quadratic. So what is the domain of f? Just for kicks.
All real numbers.
All real numbers. Now let's look at g. What type of function is g?
Radical.
It is. What's the root index?
2.
2. So do I have any restrictions that I have to take into consideration?
Yes.
What do I have to think about? What are the restrictions? How would I find them?
You would say x squared or negative x squared plus 9.
Well, can I just put that? Right?
9 minus x squared is greater than or equal to 0.
Beautiful. So 9 has to be greater than or equal to x squared. Fair?
Yes.
Then what? Okay. And so x has to be what? In between what two numbers? 3 and negative 3. So those are, g only exists here, right? The function g only exists in this interval. So this is my domain of g. So if I think about the big picture, I would say I begin with all real numbers, and then I'm going to subtract my restrictions on g, right? So my restrictions on g are this. So if I want to write it in set builder notation, I can just say this. And then do I have any restrictions on the composition? Well, let's take the composition and see. So if I'm looking at f of g, I'm looking at f of g of x. So I'm starting with f. And I'm feeding into f as its input g. How do I evaluate that?
You can simplify the first one and just have it be 9 minus x squared because
Yes.
you're squaring the radical.
Beautiful.
So then you would have f of g of x equals negative x squared.
Okay, so this is f of g of x. Do I have any restrictions on this? I do.
Oh, no.
No, you don't.
That's just a quadratic, that's a quadratic parent function that has been reflected across the x-axis. I have no restrictions on that.
So your domain would just be
So my domain is really just this. So that's how you find the domain,
So would that be x is an element of all real numbers
except
except?
you can write it like this or you can write it like that. I don't care.
Oh, okay.
Now, it gets a little bit more interesting if I give you the composition. So let's say I give you the result. I've given you h of x in each of these. You get to have the fun of figuring out what are the two original functions. Now, some people see these faster than others, like factoring, right? You see it or you don't. You may have to play with it a little bit. But if I'm looking for f composed with g, I know I'm feeding g into f, right? So this is f of g of x. So can you see what's being fed into the other way? Now, is there always one way to write it? No, sometimes there's a few different options, right? Josh, do you see it? Can you tell me what f of x is and what g of x is, so that if I fed g of x into f of x, the composition would give me this?
G of x is 2x plus 1, and f of x is x squared.
That is magnificent. You're one of those people that sees it fast. Does everybody see that?
It took me a minute to figure it out.
Right? So f of x is the big one outside. And then g of x is what I'm inputting. Again, sometimes it takes a little while to get used to these. Okay, let's think about the next one. Again, I'm looking for f of g of x. So I'm trying to figure out what f of x is, the big picture, and then the input to f of x. Any ideas, Blaine?
F of x is the cube root of x.
Absolutely correct, and therefore g of x?
X squared.
Beautiful. Excellent. Any ideas on the next one? What f of x would be and what g of x would be?
Would f of x be 1 over x?
Yes.
And then g of x would be x plus 2.
Fantastic. And again, you can do the composition to see if you get this resulting composite function. All right, here we go. Now this one, there's, some different options. Let's see. You may have to do a little bit of work to see if it really works with what you suggest. You have to play a little bit with this.
I don't know, did you check it? Did it work? Oh, I think that might be correct. I don't remember it off the top of my head, but it's something that looks like that if that's not it exactly.
So what are these papers again?
For an activity that you're going to do today and finish Wednesday, we'll finish Wednesday online, but I have to give you stuff for it because you won't be here Wednesday, right?
Is the activity uploaded onto Canvas or?
I'm sorry?
Is the activity uploaded on Canvas or will
It will be. It will be. Okay, any ideas? Anybody have any suggestions? F of x could be?
X minus 1 over x. Oh, no, sorry. Yeah, f of f of x is x minus 1 over x. And g of x is negative x squared plus 4.
Does that work?
Yes.
Okay, anybody? Oh, that's one. Anybody have anything else?
I did the opposite. I did x over x plus 1, and then g of x was
That's what I did.
negative x squared plus 3.
Yeah, I mean, take the composition and see if it works. Yeah, there's many different ones you could do, but make sure that the composition works. Okay, what I want to do next is an activity. So those of you who are not in here, I'm gonna get you started with it today, but then we're going to, it's in your notes, unless you're online, in which case, you're gonna have to work with me. I'll post it for you. Okay, so I gotta get out of here. I need to stop sharing that, and I need to, oh, how am I going to do the document camera? Poop. I didn't think about that. Oh, no. Okay, I'm going to project it here, but then this isn't going to show up on, oh my gosh. I got to think about this. If I use my video here, oh my goodness. I need my little white. There is an investigation in your notes, so it's not the next section, it's the patty paper activity. Do you see it in the packet here?
Oh, the investigation, yeah.
Yeah, the investigation. So we're turning to the investigation. And I'm going to walk you through the first step, and then you will be able to do the rest on Wednesday. Okay, so how am I going to do this? I got to get this to project here. I'm going to stop presenting here. And how am I going to do this where y'all can see it here? Y'all see it, but they don't see it. So let me move this here. Let's see how I'm going to do this. Can y'all see that? Can you see the board? I hope. Yes? All right. So the first thing, we're going to investigate what it geometrically means to take the inverse of function. So why are we going to be taking the inverse of a function? We talked about how to add, subtract, multiply, and divide. We also talked how to take the composition of the function. The next thing we're going to talk about how to take the inverse of a function. Taking the inverse of a function is going to be huge. You are going to be using this in all of your math classes from here on out. So you need to geometrically understand what it means to take the inverse of a function. So if we're looking at this, the first step of investigating is to fold a sheet of patty paper twice to form the axes of the Cartesian plane. Now, do you need patty paper? No, you could use parchment paper, tracing paper, you can even use regular paper, but we're using patty paper. Those of you who are on campus but not in the room, you can come get patty paper if you want it. Ultimately, you just have to have the answers to these, so I don't care if you use patty paper or not. So I'm folding it twice to make the x and the y axis. Okay, so I have
Wait, just one of them or all of them?
one of them. We have many investigations. This is the first investigation. You will do that for all of them eventually, but this is the first one. So this is investigation 1. Fold a sheet of patty paper, form the x and the y axis. So I labeled my axes. Now I'm going to carefully fold my sheet of patty paper to form the line y equal x. If I want to form the line y equal x, how am I going to fold it? Diagonally, right? So now I have the line y equal x. Now, I'm going to go ahead and, label, mark little tick marks. And you're going to do these a little bit more carefully once you do the activity, but I want to get you started to make sure you understand what we're doing. Yeah. So this is the line y equal x, right? So I have my Cartesian plane and I have my line y equal x. This is going to prove to be an extremely important line, y equal x. Now, what does it tell you to do next? Well, it asks you what are the characteristics of all the points that lie on this line.
Every point on this line, what are you noticing?
The same y and x value.
Yeah, the x and the y values are the same. X is y. Y is x. Literally, right? Every point on here has an x and the y value, and they're the same. That's how you would answer that one. Now, it asks you to sketch the function y equal 2x plus 1. So if I want to sketch y equal 2x plus 1, I go to the y-intercept 0, 1. And then from there, I rise 2 and run 1. So here's my line, y equals 2x plus 1. I've graphed that line. So far, so good? Yeah?
Is that the third of one?
I'm sorry?
Is that y, is it the third one or?
Y equals 2x plus 1. I went up to 1, I rose 2, I ran 1. There's my line. Jonathan, are you with me? Now, that was step 4. Step 5 says fold the sheet of patty paper along the line y equal x. To find the reflection, this is the key, the reflection of this line across y equal x. So I'm going to fold along y equal x. So I'm folding along y equal x. I notice that this piece here, I see through it, is really here, right? Isn't it here? I can see through it. This piece here is really here. So if I fold along the line y equal x, I have this line. Is that not the reflection? All I've done is I've taken this point, reflected it across this line, and it moves here. This point, I reflected it across this line, it moves here. This point, I reflected across this line, it moves here. This point, reflected across this line, moves here. Do you see how they're moving? I'm just reflecting it across the line y equal x. But you have to fold it and look through it to see. So this line reflected across y equal x gives me this line. So what I want you to do is finish this investigation. So you're going to make 2 tables of x and y values. You're going to make 1 table of x and y values for the function y equal 2x plus 1. So that means I'm just taking x values, 0, 1, 2, 3, negative 2. I mean, I don't care which ones you choose. And find their y values. Then I want you to look at this reflected line. And I want you to make a table of values, perhaps, you know, cleverly choosing my x and my y values, because the ultimate thing is for you to recognize the relationship of the domain and the range for the original function in relation to the reflected function. And you're going to notice something very special. Okay? So you're to finish this investigation, and then you are to do investigation 2. It's the same investigation, but instead of this function, I give you a different function. And then investigation 3 is the same similar investigation, except for instead of this function or the second one, I give you a third function. So I want you to do those investigations. I gave you 4 sheets of patty paper in case you mess up. 3 investigations, and then there's a summary, okay? We're going to start on Thursday by going over the answers to this. We're going to start Thursday by going over the answers to the investigation, because finding the inverse of a function algebraically is a nice little process. But if you don't understand what it means to take the inverse of a function geometrically, graphically, reflecting it, and the relationship between the domain and the range, next unit, remember what I said, logarithmic functions. They tend to be a beast to some people. We're going to have difficulty if we don't really understand this relationship, okay? So your homework for Thursday, of course, we have my math lab, but complete this investigation. We'll start with this investigation on Thursday, go over the answers, and then finish the note packets on Thursday, okay? So there you have it. So you can work on it now or as you wish. Those of you online, if you are on campus, you can come get patty paper if you want it. If you don't want it, you don't have to. Shreyas, can you tell me, is it in the notes packet? Do you see the investigation in the online notes packet?
I'm going to quickly flip through the pages because I just went back to the front page.
Okay, hang on. There's no sound for me. Oh, heavens. I'm trying to get my mouse back over here. And it's not letting me. Why is it not letting me get my mouse back? Hang on 1 second.